for lesson 9.5, there's yet another method for solving quadratic functions and finding key features of it. This one's called completing the square. We're going to use algebra tiles to help us get an idea of how to make a perfect square, and this will kind of take you back to factoring. So if we had x squared plus 6x, when we drag our tiles here, if I select that, if we have our x squared tile, and then we have 6 x's, we would want to move these so they could line up and make an actual visual square. So I'm going to line up the 6 tiles here. Keeping in mind that a square must be balanced, we see the outside of this square right here, the side length would be x, and that's why we get the name, because x times the other side length of x would make x squared. Each of these little units are side lengths of 1. So on each side of our diagram here, we have an x and 3 more. So we'll call that x plus 3, which looks a lot like what we've been working with in these 2 chapters. So now, to make a perfect square trinomial, that means if you took x plus 3 and x plus 3 and you multiplied them out, let's say we write them in factored form, what number would we want that c value to be? That is, how many little sections would we have down here to make a perfect square? That is, fill in this square. Now I could drag these all over here, but for time's sake, we would want 9 of them. So all this question is asking is what number should go here to have a perfect square? We would say 9. And that would give us x plus 3 times x plus 3. If we were to multiply that out, say with our generic rectangle here, we would get our x squared from x times x. We'd have 3x here and 3x here, which would be plus 6x, and our 3 times 3, which is 9. So we're going to be working with trying to complete a perfect square to help us reveal not only the x-intercepts of the graph, but also a vertex of our quadratic function. So for part C here, again, we could look at, they want us to complete the square. We could have our x squared, let's draw our little figure, for example, here, our x squared. And if I want 8 x's, to make it balanced, I'm going to want 4 on each side. So I'd have 4 going up and 4 on the right. And then the question would be, how many would I need here to make this a perfect square? Well, I'd have 4 in each row in each column. So 4 times 4 would be 16. There is a little formula, if you will, for completing this square, and think about it. You're always taking this middle number. So if we did, here's another example down here. If I took negative 10x, I'm going to split those equally on both sides here. So there'd be 5 on this side. And you might be asking, again, I'm drawing fast here, you might be asking, how do I do negatives? Don't worry about it too much, but remember that would be an x and a negative 5, and an x and a negative 5. This b over 2 is because we're taking half of them and splitting them half on the top and half on the side. That's why your perfect c value is going to be this negative 5 times a negative 5. It's half of your b value and then squared. So this perfect value would be a 25. Keep this process in mind as we do our solving. Notice how none of these had an equals. We were just working with a perfect square. So this example 2 looks a lot like the previous lessons we've been in, where they want us to solve a quadratic equal to 0. If you tried to factor it, nothing would multiply to 16 and add to negative 14. So factoring isn't an option. We could always graph it, but they'd like us to do some algebra to solve it. So if we use completing the square, the first thing I'm going to have us do is subtract the 16 from both sides. Let's get our x squared minus 14x, and we're going to kind of think of that little c value that we just did on the first couple slides, and we'll set it equal to negative 16. Let's begin drawing our tiles here with our x squared, and for time's sake here, I've got 1, 2, 3, 4, 5, 6, 7. Let's say that's minus 7 there. And down here, then I'm also going to have 7, 1, 2, 3, 4, 5, 6, 7. So if I was making a perfect square, I would want a negative 7 times a negative 7 to be 49. So I would like to make this perfect square on the left by adding a 49. But since we're solving, if we add it to one side, we have to add it to the other. So I'm left with x squared minus 14x plus 49 equals 33. Now we're going to rewrite this standard form that we put here on the left. This is really x minus 7 times x minus 7. So we're going to write this as x minus 7 times x minus 7. But when you multiply something by itself, we can write it as x minus 7 squared. That would equal 33. What this does for us is says if we want to solve it and keep going, remember we wanted to equal 0 to find the x-intercepts, the opposite of squaring, or the inverse operation, is to square root. Square rooting a squared will leave us with just x minus 7. And we can't forget that when you square root, like in section 9.1, that you have to have the plus or minus. We know this is going to be a decimal number, but let's leave it for now. To get x solved for, I'm going to add 7 to both sides, and my final answer will be 7 plus or minus the square root of 33. Now you might be saying, what does that mean? Well, we could split it up. Our first option would be that we could go x plus the square root of 3, or 7 plus the square root of 33. And if I did that on a calculator, approximately 12.74, then I also would have x is 7 minus the square root of 33 because of the plus and minus. Remember, those parabolas or quadratics can cross the x-axis 2 times and have 2 solutions. That's how we have the plus minus. So let's look at the graph like 9.1 told us to. If we go graph our quadratic and they wanted to know where it hits the x-axis, we should be able to see it. Well, here I have graphed x squared minus 14x plus 16, and my x-intercepts are the numbers 12.75 and 1.25 that I indicated with my math here. Again, it's always nice that we can check on our graph if our solutions come out correct. So let's try one more here. Again, that was a lot because we're completing the square and solving it. If I first add my 9 to both sides, when you're using completing the square, it's important to have just the first 2 terms, the ax squared and the bx, on the same side. So I have ax squared plus 10, or x squared rather, plus 10x, and I'm going to leave this blank equal to 9. By building my tiles, I'd have x squared plus 5 here, and x squared plus 5 here. That would mean I would like 5 times 5 to be my perfect C value for a perfect square. That would be x plus 5 squared. But if I add 25 to this side, I must add 25 to this side. And that would give me 34. Solving this, I would square root both sides and have x plus 5. Don't forget the plus minus the root 34. And my solutions would be, if I subtract 5 from both sides, I have a negative 5 plus the square root of 34 and negative 5 minus the square root of 34. Again, these will come out to decimals, but if we graphed this original quadratic, it would cross at negative 5 plus root 34, which will be a decimal, and negative 5 minus square root of 34. The last thing about completing the square that's useful is when you have a parabola, you can often talk about its vertex. So that is, when you graph it, it has a lowest point if it's a happy parabola or a positive a. So if we want to find this lowest vertex point, when we rewrite this in vertex form, so we're going to use our tiles, we have x squared, and I'd have minus 4 in these little tiles, and a minus 4 on these tiles. Remember, it's often helpful to move this 11 over, so I should do that first. Sorry, kind of all over the place. I'd have y minus 11 equals x squared minus 8x, and now I'm completing the square. My perfect C value here would be a 16. But if I add it to one side, I have to add it to the other. So I'd have y plus 5 equals x minus 4 squared. Now, that's because a negative 4 is on both of these sides. My perfect square, negative 4 times negative 4 was 16. I rewrote it in the factored form. If we subtract this 5 back over here, I'll have y equals x minus 4 squared minus 5. These two numbers here are key values in our vertex. Let's go look at our graph. When I look at the graph of x squared minus 8x plus 11, my vertex is down here at 4, negative 5. In chapter 8 rather, we learned about this vertex form, and there is my vertex. My x value is the 4, and my y value is the negative 5. So I would have my vertex at 4, comma, negative 5. We could have kept solving if we didn't have the y in here. If this had it equal to 0, they would want us to find the x-intercepts. But since they don't, we are now able to just turn our quadratic standard form into vertex form.